Hello, everyone. Welcome back. So today we're going to be talking about bimolecular elimination, which is known as E2. And so E2 is a reaction that I will once again give you the requirements for it. It requires a strong nucleophile slash base, and it requires a good leaving group. And you may notice that sounds relatively similar to SN2. That's because it is. It's the same conditions. But E2 has a lot more that you have to think about that makes it a little more confusing. So we're going to look at an example reaction of an E2, right? And let's just make one that is certainly not going to do SN2. So let's say that we took this tertiary alkyl bromide, sodium hydroxide, and we tossed it in some THF, right? What would we end up seeing? Well, what we'd end up seeing is that there would be an elimination that would occur to form an alkene, and we would get some H2O alongside some bromide, and then, of course, the leftover sodium cation. And so why does this happen over SN2? Well, as a reminder, this is a tertiary leaving group, right? Tertiary carbon with the leaving group on it. So it can't do SN2, but sodium hydroxide is a strong nucleophile, right? The hydroxide is strong, and so it's not like it's going to do SN1 either. What's going to happen instead is if we take a look at the mechanism behind how this works, essentially, in a single step, we're going to see that the alkene is going to end up forming and kicking out the leaving group all in one. So our hydroxide is going to come over and it's going to grab the proton, right? It's going to form a bond between the oxygen and the hydrogen. From here, we're going to break the carbon-hydrogen bond and we want to form the alkene. But to form the alkene, we're going to have to get rid of something on the other carbon because it already has four bonds. And so the best thing to get rid of is, of course, the leaving group. And so what this ends up doing is it generates our product with the water and the bromide, right? And so this is a single step concerted reaction, right? One step just like SN2. And the thing is, that's not the only similarity it shares to SN2, because if we're looking at an energy diagram of energy versus reaction progress, you start out with some reactants, you end with your set of products, and it has a relatively similar curve to that of SN2, right? Where we now have this delta H, we have our activation energy, everything is relatively normal, we have our transition state. But the thing is, just like SN2, our activation energy and our delta H vary based on multiple factors. So we're going to go through each of these and we're going to describe what makes E2 actually work and then thinking about E2 versus SN2 and what favors one over the other. Because it's very simple to see if we can't do SN2, of course, it's not a big surprise that we're going to do E2 if it requires a strong nucleophile and base. But what exactly is making this reaction do what it's supposed to do? Well, the first thing that we're going to take a look at is that delta H and our activation energy are dependent on alkene stability, right? Essentially, what we're looking at is as we move from regular alkenes to ones that are more energetically favorable, we see a big difference in our reaction. Because for something like a monosubstituted alkene, right, our activation energy is going to be higher. And then our delta H is going to be sometimes positive, right? Whereas if we move a little further down the line to our E disubstituted, our activation energy is going to be somewhere in the middle, and our delta H is going to be close to zero, right? So it's a bit more favorable on both ends. But as we move over to that tetrasubstituted alkene, right, the activation energy is at its lowest, and delta H is usually negative. And so essentially, what you'll find is that looking at these, they come from different leaving groups, right? So using these blue arrows to show what they would have had to come from, for this monosubstituted one, we showed up top that it comes from the secondary bromide, but it could also come from the corresponding primary bromide. For this one here in the middle, it's always coming from a secondary bromide. And for this one over here on the right, it has to come from a tertiary bromide. So notice in these cases that for our primary, secondary, and tertiary bromide, they are also in order of which is more favorable. Technically, based on this trend, we would say that there is a clear series of reactivity, right? Where we've already defined that the tertiary was better than the secondary, which is better than the primary because of the alkenes that they make. And so essentially what this tells us is that for E2 specifically, it's the opposite of SN2. Tertiary is better than secondary, which is better than primary in terms of our leaving groups. It's the opposite of SN2 once again. But there's a very important thing to keep in mind with E2, which is that primary is still possible, right? It is not as though it's impossible for us to do a primary like it was when we were looking at SN2, right? We talked about how, or sorry, tertiary and SN2 are primaries and SN1 and E1. Instead, here, every single possibility is possible. It's just that they have a difference in reactivity. Okay? So, looking at that, the more stable alkene is usually going to be the one that reacts fastest and has the best delta H. The second thing that modulates our delta H and our activation energy is that they are affected by base strength. All right? So, thinking about this idea, let's say that we were to look at an energy diagram of a couple different bases, and the idea is that all of them are being used on the same framework to provide the same reaction product. All right? And let's say that product is just a tetrasubstituted alkene, and we are going to go ahead and ignore the base hydrogen bond strength for a second. All right, just because it's going to make it a little easier for us to kind of define what's going on. So let's say we took a very weak base, right? So something like an SH minus. We talked before about how this is a good nucleophile, but that doesn't necessarily mean it's a great base, right? If we're thinking about a reaction between SH minus and something H acid, right? This would come on over, grab that proton, H2S plus the acid with a negative charge. We said that this has a pKa of 10 for the conjugate acid. All right. So it's not the best base. It's relatively weak. What we'll see is that this will go very high in terms of activation energy, and then it'll drop down to where the products are. If we were to then take a look at something like this OH minus, right, it's a better base. Because if we think about OH minus plus H acid, It does the exact same thing, but this time we know water has a pK of about 14. So it's a little bit better of a base because it makes a weaker conjugate acid. The other thing is that keep in mind when we're thinking about our differences in the OH versus SH minus, right? The SH minus is more stable. So it's lower in energy to start. And that's really important because if this is lower in starting energy and this one is higher in starting energy, when we think about this E2 reaction where we're forming the same product, these actually will have about the exact same transition state, right? We'll call them the same for right now. So automatically we can see that if we're just drawing some lines from these, we see that the delta H for the blue reaction is relatively small, and the EA, the activation energy, is huge. Versus for the red reaction, the delta H here is relatively high, and the EA has shrunk between that and the blue. This is even further exacerbated when we look at something like NH2 minus. Because here, keep in mind, it should have the exact same activation energy and the exact same product stability, but notice, or sorry, the exact same peak of the activation energy. But notice since it starts so high in energy, its delta H is huge. And then its activation energy is absolutely minuscule. So essentially, as base strength increases, the activation energy decreases, and delta H is more favorable. And so essentially, with this idea in mind, right, something like a very strong base like NH2 minus is going to love to do E2 because it has such a low activation energy barrier. Okay? So base strength matters, but another thing that matters about the bases is actually their size. All right, activation energy is affected by base size. But the thing is, the product stability is usually not affected if we're just assuming that we're using different bases but getting the same product, right? Because let's take, for example, an energy diagram where we have in the blue trace here, we will use ethanol or ethoxide. In the red trace, we will use isopropoxide, right? So it's a little bit bigger. And then the orange trace we'll use tert butoxide. So it has all of those methyl groups around. So essentially, as we go down this series, we are saying the size is increasing. Okay? So with that in mind, if all of our reactants are about the same energy, right? Because these are all just oxygens with negative charges, not much is affecting them. And we assume all of our products are about the same energy. For the blue trace, it's going to be very easy for it to come in contact with some type of hydrogen. Because remember that the transition state is all about the single step that we're looking at, where essentially we are trying to get whatever oxygen it is close enough to that hydrogen without bumping into other stuff. All right. So looking at this further, that means that the isopropoxide has a steric component that makes its activation energy higher. And that means that the tert butoxide, right, we can create some lines here because we don't have enough space to show the top of the peak, is even higher. So tert butoxide has the highest activation energy, right? And we know based on SN2 that also sterics cause a big difference. So essentially, since the base here is sterically bulky, our transition state is crowded and unstable. So we see three factors here that play a big role in reactivity. But the thing is, if so many factors change reactivity, how do we know when it's an E2? Well, the first thing we need to do is we need to actually redefine our idea of our nucleophilicity scale, right? So looking at our old nucleophilicity scale from the SN2 lecture, essentially what we said was there's a line in terms of nucleophilicity that on the right-hand side is the most nucleophilic, and then on the left-hand side is the least nucleophilic. And we made a dotted line that essentially said everything below this is a weak nucleophile, right? And so they won't do SN2 or E2, which is nice, right? Because we need something strong. On the right-hand side, though, these are our strong nucleophiles. With this in mind, we ranked these in terms of a lot of things. We did some size, we did some electronegativity, stuff like that. And we came up with this idea that all the way at the top was generally our sulfur nucleophiles. Then we have Cn, we have I minus, RO minus, have our NH2, and then our Cl minus. Right? And we said that even though nucleophilicity generally scales with basicity, it doesn't always. Right? And so this idea here doesn't match a basicity scale. Rather, if we were to do that, we would find some interesting trends, right? Because thinking about a basicity scale, which we'll do in blue here, going from least basic to most basic, this is practically, thinking about it, our pKa table. But the thing is, with nucleophilicity, remember we talk a lot about our negatively charged things being strong. So we're only worrying about things that have a negative charge. Well, all the way over here on the left with the least basic, that is going to be things like iodide. Because remember, the iodide is a conjugate base of a strong acid. So it's all the way over here at being a really crappy base. And so as we move down the line, we see that our nucleophilicity scale and basicity scale are a little different for all of the things with negative charges. And remember when we talk about the R groups, it can be any types of carbons, right? Just not heteroatoms. Carbons are hydrogens, just not heteroatoms. So we have this as our basicity scale. And I'm going to draw two lines down this basicity scale. One of them is going to go right in here. And what this is showing is this is essentially showing the point that something is too weak of a base, right? We would say that these over here are weak bases. And what weak bases do is they will actually only do SN2, right? Because they can act as strong nucleophiles, but they can't act as strong bases. We'll draw another line right here. This is where we get our average bases, right? These are going to do a mix of SN2 and E2, right? Now, that being said, that is not entirely true about all of these. Because notice that when we say this idea of doing a mix of SN2 and E2, we can imagine that this R group on the oxygen could be like ethyl, It could also be something like that tert butyl. And if you think about SN2, remember that sterics are incredibly important. The more sterically bulky something is, the less it can do SN2. That's also true here. So looking at this idea, there's actually this dividing line between that and the other bases that are over towards the right. Because essentially this is too bulky to do SN2, right? It's going to be too high of energy. But as we know with E2, a lot of it is, even though it may be sterically bulky, it's still possible. Then on the right-hand side here, these are what we would call our strong bases, right? And these right here only do E2 because they are so incredibly basic that they have this very high energy, as we discussed up here in the second part, that the activation energy is just a little bitty hump versus if they were doing an SN2, it's still very high because it has all of that steric bulk. So, what does this mean in terms of energy diagrams with these? Right, let's take a look at one on the very far left-hand side. Right, if we're thinking about the energy of a reaction with, let's say, iodide, right? So we'll do, make sure to label this. This is with I minus. And we'll do a blue trace here for if we were doing SN2. And we will do a red trace here for if we were doing E2. So we know that iodide is not basic, right? Which means that even though both of these will start at the same reactant level, they actually end up with very different levels of their final product energy. Since it's such a bad base, it's actually going to be more endothermic because the bond between the hydrogen and iodide is going to be very weak. Versus an SN2, it's actually going to be relatively favorable. So even though both of these may end up with relatively similar activation energies, SN2 is so much more favorable because it has a highly favored delta H, right? So essentially what we're saying there is just due to I minus being a bad base, E2 would be endothermic and disfavored. All right, let's look at the opposite end of the spectrum. Let's come in with one of those can only do E2, right? And we'll use NH2 minus as an example. Right? With this, we already described above what happens to your activation energy as you use these more unstable bases. It essentially drops for E2 because you raise it up so much. But in this case, both reactants will be the same energy. If we think about it, a substitution is always going to be a bit more stable than an elimination, right? So the product in this case of the elimination is technically less stable in terms of enthalpy. But the thing is, this is an example of even though the product enthalpy is more uh, or less stable, it has such a low activation energy, whereas Essence 2 still has its very high peak, that the higher energy product is actually technically favored due to the better activation energy, right? So in this case, um, E2 happens faster and is still favorable by delta H, thus it occurs over SN2. Okay, so with that idea in mind, right, we've kind of described the idea behind why something that's not very basic would be bad because it's more endothermic. Something that's very strongly basic is better because it has such a low activation energy. But what about those bulky and small bases, right? So this is where things get weird with E2. Because in E2, we have essentially started to look at the exact same ideas as E1, right? Where we want to form relatively stable alkenes. And so if we were to take something like this alkyl bromide and react it with ethoxide, we would do an E2. And so, as per usual, we would look and see if there were any alpha carbons with alpha protons. There are. And we want to find the one that's the most stable. And so, looking at all of our alpha carbons over here, we would see that this one that I've highlighted would be the one that would form a trisubstituted alkene. And that's exactly what this would do. But what would happen if we did this exact same reaction, but we brought in tert butoxide? We actually end up with a different product. And so this is where E2 becomes a little more complicated than E1, because based on our base size, we form different products. The question is why? Well, let's think of it this way. Looking at an energy diagram, as we always do for these types of reactions, we can imagine that if we were to do our red and blue trace, right, where blue we're just going to say is going to be the blue reaction that we draw out, and then red will be the red reaction that we draw out. We're going to draw some transition states and hopefully make a little bit of sense out of this. So, for the blue reaction, this is going to be if we were using a big and bulky base and trying to deprotonate the product that we actually form there, right? Looking at this, we would see that here's our bromine, and it's pulling from this alpha car proton here to actually form the base, right? So what this is doing is essentially our base comes in, grabs that proton, forms the double bond, kicks out the bromine. We end up forming a less stable disubstituted alkene along with our alcohol there. In the transition state for this reaction, what we would see is that our oxygen is trying to take or form a bond with the hydrogen. The carbon-hydrogen bond is breaking. We are forming the alkene, so the CC bond, and we are breaking the carbon-bromine bond. So there's a lot of bonds forming and breaking at once, right? We show every single one of those with those dotted lines. And we would see that the oxygen has a partial negative and the bromine has a partial negative because I didn't show it up here in the products, but we do have the Br minus that's coming into play. So essentially, this transition state is showing that this is relatively fine, right? There is little steric interaction because it's deprotonating from a primary. And from that primary, the only other things that are there are two other hydrogens. So essentially, we're saying that since we're deprotonating a primary carbon, there's little steric interaction, which is great, right? That means that our activation energy is going to be relatively low. Versus if we were to do our red reaction, which is if we tried to take that same bulky base, but instead deprotonate this secondary carbon, which would lead to our technically more stable alkene. What would that look like? Well, we would grab that proton, we'd form the double bond, we'd kick out the bromine, just like we did in the previous one, and we would form that more stable trisubstituted alkene. But in our transition state, what we would see is that now, instead of just being like that primary, we have a situation where this oxygen is now getting a little close to some things, right? The carbons that are attached to the backside of where the oxygen is are now kind of butting up against these other carbons here, right? Because of that being a secondary carbon, it has that extra bulk that then interacts with our base, right? So this is some steric strain, which means it's going to have a higher activation energy. So looking at these in terms of our reaction coordinate or energy diagram, they would both start from the same reactant energy. We know that the blue reaction ends up forming a less stable alkene, so its products are going to be about here, and the red reaction is more stable, its products are going to be about here. We also know, based on what we drew, that the blue reaction is going to have a relatively modest activation energy, but the red reaction is going to have a very high activation energy due to the steric bulk. So we would say that in terms of these two reactions, the blue one happens faster because it's more favorable by activation energy. So we would say that the blue reaction is favored kinetically, right, due to its low activation energy. But we would say the red reaction is favored thermodynamically due to its negative delta H, right? More negative. Both of them are in this case are negative. Here's the thing, right? The activation energy is directly impacted by how much bulk you have around your base. Because you can imagine if those other two carbons weren't there, this reaction would also have a relatively low activation energy, right? Versus the blue reaction here, they would be about the same. But the fact that we have those extra carbons around the oxygen that's acting as the base makes it this higher energy, more steric strain in our transition state. So what this does is it presents us with this idea that the base strength or the base size actually impacts which product distribution we're going to have, as we saw up here, right? Because those smaller bases, they have an easier time reaching those hydrogens without causing any steric strain, but the bigger bases have a bit bigger of a problem with reaching those hydrogens. And there's actually a name for both of these reactions as we have them drawn, and those are the Zaitsev and Hofmann products, right? So Zaitsev essentially found that if you're looking at a reaction, that the Zaitsev product for an E2 is the thermodynamically favored alkene. All right. And this usually results from small bases. Now take that and look at the opposite of it. And this is where we get the Hofmann product, which is the kinetically favored product. Right? So it is the kinetically favored alkene, and it usually results from bulky bases. Right? So depending on the base that we use, we are going to get one of these two products. And it is going to be much more favored than the other one, as we are saying here. So looking at this idea, we are going to look at some bases that form the Zaitsev product. And then we're going to look at some that form the Hofmann product. All right. So for the Zaitsev product, we're usually looking at things that are relatively small, right? So we've already discussed one of them being the ethoxide, right? This has a linear chain which is considered small, right? Because those carbons can move around and not really interact with many things. Some other small bases that we can look at are going to be things like NH2 minus, right? That one's very small. Those hydrogens aren't going to do much. OH minus, and other linear chains, right? You can have something that is technically a very large molecule, like this one that has many, many carbons. It's still considered small though, because that chain is linear. On the other hand, for the side of Hoffman, we've already discussed one of these, right? It is that tert butoxide. Because when looking at this, that carbon right there is branched, right? And so branching, where you have multiple carbons coming off of the same carbon, is considered large. Okay? And so looking at this, we're looking at things that are going to be branched. So something like isopropoxide, it's branched to that carbon. It's a secondary alkoxide, so it's going to be considered large. We have things like these amides or amides, where it has this negatively charged nitrogen in it, right? That is considered to be bulky because it has those branching side arms hanging off of them. Same thing with this idea of a really weird looking base that has silicon in it, but it's still the same idea. It's a negatively charged nitrogen that has a lot of steric bulk around it. So essentially, what we have to get used to is we need to think about when we're doing E2 reactions, will this favor the most substituted alkene or will it favor the least substituted alkene? Because keep in mind that this is completely different from E1, where no matter what you use in an E1 reaction, you will always form the most stable alkene. That is not true in terms of E2. All right. The other thing for E2 is that there are some stereochemical implications. All right, so essentially, just like SN2, E2 needs a backside attack to kick out the leaving group, right? So it's just like our good old SN2, we need the backside attack. But what this looks like for E2 is a little different. What we see is that if we were to draw out a molecule very large, so that's easy to see, when our base comes in and takes the proton, essentially the electrons from the CH bond are going to have to come on over and backside attack to kick out the bromide, right? Or the leaving group. Because in this case, notice that if we were to draw a dotted line here, where the electrons are coming from that hydrogen are 180 degrees from where the bromine leaving group is. All right. And that being said, there's a very important statement to be made here, which is for the electrons to be 180 degrees in terms of its attack angle, the CH bond has to be 180 degrees from the carbon bromine bond. Okay, so what does that mean? Well, this is going to be another flashback, and the reason that we talk about a lot of the things we do in this class is because it always comes back. And in this case, it is Newman projections. Because if we're looking down this bond, we're essentially talking about the dihedral angle between the hydrogen and the bromine, right? A Newman projection looking down this bond would show us that if we're just assuming the groups on the sides are R's, right? Our bromine and our hydrogen are in plane, so they are the top and the bottom here. We see that the dihedral angle, in this case between these two, is 180 degrees, right? And if our dihedral angle is 180 degrees, that is essentially what we called anti when we talked about our Newton projections, right? We talked about the anti form being the one in which the largest groups were 180 degrees from one another. In this case, we're saying the hydrogen has to be anti to the bromine. And this actually has a name in terms of when we're talking about E2, and it is called anti-periplanar which essentially says that you need to have the things 180 degrees for their angle within the same plane. So whenever you hear antiparaplanar, you want to think the dihedral angle is 180 degrees. And the thing about E2 is E2 requires this to be true, right? So it requires the hydrogen and leaving group dihedral angle to be 180 degrees, aka anti-periplanar. Okay, so why does this make a difference? Well, it's because you may not always have situations where your dihedral angle is 180 degrees, right? We're going to take a look at a couple of these ideas. So we're going to move on to some examples of E2. So first off, let's take a look at one where we're going to start with some stereochemistry on here. It looks like this. So let's say we took this molecule and we reacted it with sodium amide, NaNH2. The first thing that you want to do before you even start to think about any of these considerations that we're bringing up is that you need to first identify what type of reaction this is going to be. You already know from this lecture it's going to be an E2 reaction, right? I forgot to put a solvent. There we go, DMF. And so in this case, we have to ask, okay, if it's E2, the first thing we need to know is it going to favor the Zaitsev or the Hoffman product? NaNH2, which is just essentially NH2 minus as the base, this is relatively small, right? So it favors the Zaitsev, aka the most substituted alkene. Okay, so if it favors the most substituted alkene, the next thing you need to do is you need to look at your leaving group, which in this case is on a secondary carbon, and you need to look alpha to it to see which one is going to end up making the more substituted alkene. We see it's going to be the one to the left, right? Because there's that CH3 there that counts as a carbon. That's going to give us a tri-substituted alkene, whereas the alpha carbon to the right would only give us a mono-substituted alkene. So now what we do is once we have those things in mind, we say, okay, we've picked which we want to eliminate from. We need to take a look down this bond and see what our Newman projection tells us. Well, in this Newman projection, what we see is that if you draw it out, we have our ethyl facing that way, right? Because we want to do our in-plane substituents first. We have our CH3 on the back carbon facing upward. The wedge on the front, if we're looking down that bond, will be to our right. So there it is. And then we have our hydrogen on the dash, so it's on the left. Bromine's on the wedge on the back carbon, so it's on the right. And then the hydrogen there on the left. We see that indeed, in this case, our hydrogen and our bromine are 180 degrees, right? Which means that we are good to perform an E2 reaction. So what that'll look like is we'll draw it on a molecule that is not as incredibly marked on. Our NH2 minus is going to come in and act as the base. It's going to grab that proton. We're going to form the alkene and we're going to kick out the bromine all in a single step. And that is going to generate this tri-substituted alkene. All right. And then we also have NH3 and sodium and Br minus. But essentially, the main component that we care about is the E alkene, right? Our tri-substituted E alkene. So that's great. That was very easy. What happens if it gets a little more difficult and we don't have what we want, right? Let's say that the stereochemistry was slightly changed. Let's say instead of the hydrogen being on the dash, the hydrogen was on the wedge. Well, we can skip over a lot of the stuff that we thought of at first because I'm just going to give us the same conditions in NaNH2 and DMF. But if we do our Newman projection, looking down this bond, what we would see is that it's not going to necessarily align with what we originally had done, right? We would see that from this, if we were to draw our Newton projection, our ethyl would be here, hydrogen here, CH3, bromine, CH3, and H. Right? Looking at this, what is 180 degrees from the bromine? It's the CH3, right? So it's not anti to a hydrogen. So that technically means we can't do E2 here. It is not possible from this current position. But as a reminder, think back to the old lectures. Conformers can rotate, right? So, but remember, conformers rotate. And that's important because what we can do is we can actually do a rotation on this conformer. And what we'll do is we'll take our front carbon and we'll move the hydrogen 120 degrees over to here. CH3 will go that way, and then the ethyl will go that way. And by doing that rotation, what we've done is we've now set ourselves up to where the hydrogen is in this position, where it is now anti to the bromine, right? But remember, the back carbon did not change where everything was. So now that this is anti to the bromine, it's good to go. But the thing is, since we rotated this, it does not necessarily look the same as what it did before. All right? Looking at this in its actual bond line form now, we would find that it has essentially slightly altered where things sit on that front carbon to where now the hydrogen is on the dash, the ethyl is on the wedge. And so notice that by rotating this conformer, we essentially did the same thing that we were doing a lot with stereochemistry. We were taking this group, moving it to here. We were taking this group, moving it to where the planar thing is, and then taking this group and moving it onto the wedge, right? And this does affect our reaction outcome. Because looking at this now, if our NH2 minus comes in, acts as our base, grabs that proton, we form the alkene, we kick out the bromine. Notice that the alkene that we have formed, because all of our stereochemistry disappears on the alkene because it is sp2 and it's planar, now the ethyl group is pointed upward where this is now Z, right? So essentially, depending on the stereochemistry, you can get either the Z or the E alkene, right? So what we're saying is that the stereochemistry of the hydrogen and leaving group determine the alkene stereochemistry. So you always need to make sure that you're paying attention and making sure that you are grabbing the anti-hydrogen to the bromine. Now, as a reminder for E1, because again, people like to compare this to E1, and I want to make sure that you're well aware, E1 can only form the E alkene, right? There is no ability for E1 to form the Z because it's not the most stable. E2, on the other hand, can form the Z because it has to. It has no other option. All right, let's look at another one that's very similar. Let's say we take this same molecule and then we instead react it with LDA, which is this lithium attached to the nitrogen, a couple isopropyl groups. So, looking at this reaction, first thing that we need to think of is, all right, well, our base, our active base, is actually this nitrogen with a negative charge here. It's just a lithium with a positive charge right there. This, unlike the previous ones we've been using, is a bulky base, which means it favors Hoffman which is the least substituted alkene. So, in this case, if we're thinking about where the least substituted alkene is, right, the stereochemistry that's shown over here on the left actually shouldn't matter because that's still going to form a trisubstituted. Whereas if we go towards the right-hand alpha carbon, we would form a monosubstituted alkene. And the benefit of going towards this right-hand side is it makes our stereochemistry argument very easy because looking at it, it has a hydrogen in plane, it has a hydrogen on a dash, it has a hydrogen on a wedge. There are hydrogens everywhere, right? And it makes it really easy because essentially, when our base comes in here, no rotations need to be done. There's guaranteed to be a hydrogen that is anti. In this case, it is the one on the dash. And so we end up with our final product being this here. It's monosubstituted. There's no other alkene that's even possible, right? Because it is the Hoffman product. So keep that in mind. And notice one thing that I said right here that's very important is if the bromine is on a wedge, the hydrogen must be on a dash to be anti, and vice versa. So, one thing to keep in mind with a lot of these reactions is that whenever you're looking at the stereochemistry, you need something to be anti-paraplanar. Also, don't forget that the base matters a lot in terms of whether or not you even have to care to begin with. All right. I got one other example before we move on and talk a little bit about rates and such. And that is going to be for this reaction here. I forgot to give a solvent up top. It could be anything. We'll just do THF. So looking at this, we have the sodium amide with DMF. In this case, the sodium amide, this is, of course, a small base, which means it's going to form Zaitsev products. And then looking at our alpha carbons, we have one here and one here. All right. And so these would both end up forming trisubstituted alkenes. But looking at these, we have something interesting that's happening. Because if we draw out where the hydrogens are on each, this one has a hydrogen on a dash, and this other one has a hydrogen on a wedge. Now then, what's weird about this, and this is why chairs are a little funky, is that we can't necessarily rotate this hydrogen up here into a position where it's on the wedge, right? We can't rotate to be on a wedge. And the reason for that is because this ring is locked in place, right? If we wanted to try and rotate this carbon upward, essentially the whole ring is going to come up with it. It's just not possible. And so in rings, we have what we call this locked stereochemistry, right? Whenever we expose this to the NH2 minus, there's only one thing that can occur, right? This hydrogen right here is anti to the bromine. The other one is not. And so because of that, the NH2 has no other choice but to deprotonate here, and we end up with this being the only product. Right? There is no other possible alkene we can form. The other interesting part about it is if we were to look at this in terms of chair conformers. Because remember, everything comes back in this class. What we would see is if we drew out a chair of this, we would find that for our first chair, we could draw it to where we have sort of this bromine on the dash, so it's pointed downward. we'd have a CH3 pointed up here. We would have a CH3 pointed down here, and then we'd have our hydrogen here. If we were to look at the Newman projection for this, what would we see? Well, we would see essentially this here, in which on the front carbon, this is if we're looking down these two carbons here, right? We would see on the front carbon, CH3 is pointed down, H pointed right there. The H on the back is on axial, Br here. We're not going to worry about where the other CH3 is. We're just going to fill in some other things because that one, of course, doesn't matter. We'll even erase it from up here. We see that this can't do E2 as it stands, right? So this one can't do E2, right? And the question becomes, why? Well, if we look at this, where's the bromine? It's anti to a carbon, right? It is not anti to a hydrogen. The hydrogen that we want it to be anti to is right here in the equatorial position. The only way we can do E2 here is if we were to do a chair flip. With the chair flip, what we would see is that our hydrogen is now up on the axial position, CH3 right there. The bromine is down on the axial position. And if we were looking down now these bonds for our Newman projection, we would see that essentially front carbon's pointed up on this one. So bromine's down here, hydrogen's right here. Front carbon has the CH3 right here. Hydrogen, 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 hydrogen. We see that now the hydrogen and the bromine are anti to one another. And it brings up an interesting point. Notice how in the case of the one over here, these are both currently equatorial. And then in the case of these over here, these are both axial, right? What this means is in cyclohexanes, backside attack can only occur when a group is axial. There is no other time that it's possible to do a backside attack. Now, that is going to be a well touched on subject whenever it comes to the actual practice problems we have. Okay, so keep that in mind. But otherwise, just keep in mind that since chairs can't rotate, only the hydrogens that are already in position to do elimination will be able to. Okay? All right, next thing is the rate of E2. So as a reminder, this is a single step concerted reaction, which means the single step is the rate determining step. And of course, that step is the only one which requires our base to come in and interact by grabbing that proton, forming the alkene, kicking out the bromide. And we know whenever we're setting up these rate reactions that we have just the reactants acting as the concentrations in our rate. So essentially, when we're looking at rate for an E2, it's the same as an SN2 where it requires both the thing with the leaving group and, in this case, our base concentration. And so that's why we call E2 bimolecular, because there are two molecules that interact to form our rate. So that is everything to do with E2, right? We're looking at you have to have anti-paraplanar hydrogens. The base size determines the stability of the alkene that you form. Tertiaries react faster and secondaries react faster than primaries. Nothing's off limits. So how does all of this relate? And this is where we finally get the everything together to where we can actually look at the big four reactions that we've been talking about recently. So an overview of the big four. Essentially, we can make one dividing line immediately. All right. That is between what we'll call strong nucleophiles and weak nucleophiles. Right? This division automatically sets us up where we kind of know what sits in a couple of these categories. For things that require strong nucleophiles, we're looking at SN2 and we're looking at E2. For things that require weak nucleophiles, we are looking at SN1 and we are looking at E1. And while this looks like it would be a square, remember that E2 and SN2 have a very fine line that just says if one's happening, the other one's not. But then SN1 and E1, the line is very blurred, right? We can count it as more of like a dotted line because we know that these two are always together. Okay, so looking at what favors each of these. For SN2, let's think about where the leaving group is going to sit on this. SN2 loves primary leaving groups. It's okay with secondary leaving groups. But essentially, we can't have any tertiary leaving groups, right? That is the big thing about SN2 is if you have a tertiary leaving group, it just can't happen. The opposite's true for SN1 and E1, right? They are happy with tertiary or secondary leaving groups, but no primary leaving groups. All right. So that's the same for both of them. All right. E2, on the other hand, we've already talked about nothing's off limits. So tertiary is better than secondary, which is better than primary. But essentially, all are possible. All right. The next thing is if we want to think about the products that are formed from these, right? We have for SN2, always inversion of stereochemistry, whereas SN1, it always forms racemic mixtures. For the eliminations in the alkenes that they form, essentially E1 we know is always the most stable alkene, no exceptions. And then for E2, it's a little bit different because base size determines alkene stability, right? So to figure that out, you're looking at Zaitsev versus Hoffman products. And then thinking about also the idea that you need an anti-paraplanar hydrogen, that's what determines if an alkene is E or Z. And then last but not least for each of these, they do have some solvent specificity. Now keep in mind, this is the least important piece of each of these. The things I've already listed above are more important. But in terms of solvent, SN2 wants polar aprotic solvents. SN1 wants polar protic. E1 also wants polar protic. And we didn't talk about it much this lecture, but you can probably assume the E2 being like SN2 also wants polar aprotic solvents. But it's relatively necessary for E2 because, of course, these are very strong bases and you don't want to have an acid in solution. So, overall, this is what the big four is all about. So, here's what I recommend. because this week we're going to have two practice worksheets because this is such a big amount of material that we haven't been able to practice much throughout the class because of how long each lecture is. But essentially, what those worksheets are going to do is they're going to set up this entire idea of SN2, SN1, E2, and E1, and it's going to allow you to practice these reactions with just actual reactions that they don't tell you exactly what's going to be the outcome, because I'm also not going to tell you what the outcome is going to be on the exam. You will have to use the information provided to identify which of these four reactions is most likely given the conditions that you have, and then you're going to have to then take that and draw the products that should result from said reaction. So I highly recommend doing those practice worksheets because they'll give you practice with that. And then that'll, of course, bleed in to the quiz that comes this following week as well as your assignment. So with that being said, I will post another video going over some of these types of reactions here soon, but it's going to be going over the ones on your practice worksheet, so try and do them in advance. That being said, this is the end of that four lecture series of what is a relatively difficult part of this semester. Make sure you practice it because next week we're going to be hopping into other types of reactions that are not just these four, and they will have very different reagents that are provided for each, unlike these that are very similar. See you next time.